Hello and welcome back to Dynamics System Modeling. In today's session we will be discussing transfer functions. And in a simple definition, transfer function is given by Laplace transform of the response of the system. And those transfer functions yield very important information about the system's behavior, and they simplify the computation of the output response. However, in today's session we will only focusing on how to derive those transfer function, and in the upcoming session we will do the analysis. So assume you have a system, okay, and this system you have an input f of t and the output is x of t, right? So in the Laplace transform what we do, we derive the differential equation, then we perform the Laplace transform in which the time domain becomes in the frequency complex domain, S domain, and the x of t becomes x of s. Right? And the relation between the input and the output is some function called h of s. This h of s, okay, multiplied by f of s, so f of s multiplied by h of s is equal to x. Right? Then h of s is equal to x of s over f of s. X of s is the output and f of s is the input, and those are expressed in the s domain, and this is what we call the transfer function. So the output over the input is called the transfer function. Great. Most importantly, remember, in order to derive the transfer function you should be assuming zero initial condition. So your analysis of the system must be started from rest. So you will not assume any stored energy previously in the system. So to make our understanding concrete, let's go into a practical example. Consider the following system. You have a mass, an input force f of at, and you have two outputs, the displacement of this node and the displacement of the mass as x1. Okay, but we are interested only on one output. The output of the system is x1, and of course we have zero initial conditions. Okay, and those are the parameters or the mechanical component of the system are given to us. Okay, so the first step, we draw the free body diagram as we have noticed from previous sessions. Okay, this is mass f of at. We have k1, x1 minus x2, the friction, and the D'Alembert law. The node, this node, okay. So for every action there is equal and opposite reaction. It is x1 minus x2 in the opposite direction. P2 is acting in opposite direction, x2 dot, k2, x2. Now we write the differential equations. Okay, now for simplicity I will denote x1 of s as x1, capital X1, so in S domain, and similarly x2 of s is x2. Now in order to obtain the Laplace transform of x1 double dot, we will be using the table. It is given by s square x of s minus s x0 minus x0 dot. So m1 s squared x1, it is x1 of s, but we will be writing it from now on x1 only, minus s x1 of 0, this is in s domain, this is in time domain, minus x1 0 dot, plus the Laplace of x1 dot is sf of s minus f0 plus as we mentioned in transfer functions, the initial condition must be set to 0 because our analysis must analyze the system starting from rest, and next time it's not necessary to write those initial conditions, okay, once we are asked to obtain the transfer function. Now, because we are interested in the displacement x1, so we could eliminate x2 and substitute it. So from this we obtain x2, and then we substitute it in the first equation. And I will also substitute the parameters by their numbers. So now we can substitute it in the first equation. Okay, let me write it down. Now we will have a common denominator, s plus 2 multiplied by this. Then x1 over f of a, which is the transfer function, is equal to s plus 2 over s cubed plus 3s squared plus 3s 2 minus 1 plus 1. Okay, so this is called a transfer function. So it is the output over the input. Okay, now let's take an electric circuit, alright, in this like this example, and we have the input EIT and we have the E0, right? Now we can determine the differential equations as we did in the previous example in the mechanical system. We write the differential equation, then we do the Laplace transform, then we want to correlate the input to the output in S domain, alright? However, in electric circuit it's easier for you to convert each element directly into a Laplace transform. And for instance, let's take the R. We note that the voltage over the resistor is equal V R1I, right? Then V, the Laplace of V is V of S, R is constant, it will remain I of S. Then the Laplace of the resistor is V over I in S domain, which is the output over the input, right? So we have the resistor, okay, so which is equal to R1. So this will remain R1. Yes? I'm just recording, nothing. Thank you.
Sorry.
No problem. Okay, now return back. Okay, we note that I, okay, or V over the inductor, V of L, equal LdI by dt, and this is equal to VL in S domain equal L as I of S plus, of course, L I0, this is equal to 0, 0 initial condition, and then we have VL I in S domain is equal to Ls. Okay, so the inductor, alright, becomes a resistance of term L of S in the S domain. Okay, this component. For the capacitor, it is I, or yes, I equals C d V by dt. Again, I equals CS Vs 0 initial condition, V equal over I in S domain, 1 over CS. So we could replace L by Ls. R1 stayed the same, and the capacitance will become 1 over CS, and R2 will stay the same. Now, because this is a resistance, and this is a resistance in S domain, then we can say, and this is E0, okay, EI will become EI in S, E0 is E0 in S domain. Again, for making it short, we will denote E0 of S as E0 only, okay? So this node is E0, because if this is EA minus ground over, it is E0S, so this is E0. So we could say E0 minus E1, and those two resistors we could sum them, Ls plus R1, okay, E0 minus E1 over Ls plus R1 plus E0 minus ground over 1 over CS, E0 minus ground over 1 over CS plus E0 minus 0 over R2. So let's take E0 as a common. 1 over Ls plus R1 plus CS plus 1 over R2, which is equal to E1 over Ls R1. Common denominator, okay. Okay, so in order to obtain the Laplace transform, the transfer function, the transfer function is the output over the input in S domain, okay, which is equal to R2 over this part, let's do it, R2 LC Alright, so this is the transfer function of this electric circuit, which correlate the input to the output in the S domain. In the upcoming session, we will be discussing the response of those systems and how we analyze the response of the system for a given input, either in the electric circuit or in the mechanical system. Okay, so we have the input is given, either unit, ramp, or whatever, and then we could analyze the output. And actually, we will also not only analyze or determine the response of the system E0 in the time domain, but as well we will be discussing the transfer function itself. So this component will be giving us a very important information about the system in order to understand it better. Thank you, and see you in the second part of this lecture.